What actually happens at the end of the universe? Or, have you ever wondered if a massive population eventually stabilizes? What about a cooling nuclear reactor? Does it ever hit a final absolute temperature? To answer these massive questions, we've got to go to the very edge of mathematics, the place where X grows literally forever. Welcome back, future doctors and engineers. Are you ready for a new mathematical thrill? Let's get right into it. Over at NASA, engineers have to calculate something called the escape velocity. They absolutely need to know exactly what happens to an object's trajectory as its distance from Earth becomes infinite. Think about it. If the math fails out there in the infinite horizon, the whole mission fails. But hey, before we blast off into our own calculations, I want to give a massive shout out to our calculus heroes who completely crushed the continuity challenge in our last explainer. You guys know exactly who you are. All right, section 1. The core concept, the horizontal asymptote. So the line y equals L acts like this invisible boundary. The function gets closer and closer, but never quite breaks through it. James Stewart's calculus defines this beautifully. When x goes to infinity and the function f of x settles on a specific height L, we call the horizontal line y equals L a horizontal asymptote. Think of it as the function's final resting place, no matter how far out on the x-axis you decide to travel. And this brilliantly illustrates how a function can get completely locked horizontally between two specific values as x just grows forever. Take the inverse tangent function, arctan of x. As x heads toward positive infinity, the function flattens out, trapped right underneath a ceiling of pi over 2. And as x heads to negative infinity, well, it's supported by a floor at negative pi over 2. It's an infinite journey, but it's perfectly contained by mathematical walls. How cool is that? Moving right along to section 2. Level 1. The divide and conquer strategy. Okay, the rule to defeat these tricky rational functions is actually pretty simple. Step 1, you identify the absolute highest power in the denominator, something like x squared. Step 2, you ruthlessly divide every single term in both the numerator and the denominator by that x squared. And step 3 is where the magic really happens. As x gets undeniably huge, the smaller fractions, like 1 over x or 2 over x squared, they simply die out to 0. They just vanish. By dividing out the leaders, a massive, totally intimidating rational function just perfectly collapses. All those trailing fractional pieces become 0. So if you had a 3x squared on top and a 5x squared on the bottom, all the mathematical noise just fades away, leaving a clean, crisp 3/5. And that 3/5? That is your exact horizontal asymptote right there. Now I want you to pause this explainer for a second and really think about this. Who wins the infinity race if the power on top is heavier? Like if we have an x cubed on top but only an x squared on the bottom, does it settle into a nice neat number? No way. The top grows vastly faster, meaning a function races away to infinity. Absolutely no horizontal boundary can hold it back. Watch out for section 3. Warning, the zoom trap. Listen to this warning because we are entering dangerous territory where your calculator will outright lie to you. If you try to use a graphing calculator to find the limit of e to the power of 1 over x as x approaches 0 from the right, the calculator just draws a vertical line and completely gives up. The pixels literally cannot render it. But analytically, using Stewart's logic, we know that as x gets incredibly small, 1 over x explodes to infinity, which means the whole function skyrockets boundlessly. The machine fails to show the infinite explosion, but our analytical logic, it never fails. Let's level up. Section 4, Level 2, the square root trap. This is an algebraic pitfall that catches even the best students. The absolute most critical rule to remember here is that the square root of x squared is the absolute value of x, meaning you absolutely must flip the sign if you are heading toward negative infinity. If you just blindly pull an x out of a square root and ignore the fact that you're traveling into the negative quadrant of the graph, your entire calculation is going to be totally upside down. So applying this securely to our problem, we follow the exact same core logic. Step 1, divide by x. Step 2, we safely pull it under the square root as an x squared, assuming of course we are heading to positive infinity where x is positive. And step 3, exactly like the divide and conquer method, we let those smaller fractions with x in the denominator just melt away to 0. This flawless execution leaves us with another beautiful, perfectly boxed in answer. If our leading terms inside the radical gave us a 2 and the denominator a 3, all the chaos clears, leaving us exactly with this square root of 2 over 3. No calculator required for this, just pure, unbreakable logic, helping us find the exact horizontal limit at infinity. All right, here we go. Section 5. Boss Battle, the final challenge. You've survived the traps, but are you ready for the final test? What happens when you encounter an infinity minus infinity situation? You definitely can't just subtract them and get 0. I want you to use the rationalization trick we learned in our previous explainer for this exact scenario. Remember? Multiply by the conjugate. The very first person to post the correct, fully derived answer down in the comments gets a spot on the next leaderboard. Before we wrap up, I want you to think about something really profound. If infinity isn't a number, but a direction, what does it mean that our mathematics allows us to perfectly calculate the exact destination of a never-ending journey? It essentially means human logic can literally contain the infinite. Wild, right? To help you conquer these infinite boss battles, make sure to download your cheat sheet in the description below. Share this explainer to help your classmates survive that nasty square root trap, and most importantly, stay dynamic, because our next step is derivatives. I'll see you there.